Hello, I am Hyunmin Lee, a junior from the Hockaday School, and my project is about the diagnosis of Parkinson's disease through spiral drawing classification via VGG19 and Anugen. Parkinson's disease, also referred to as PD, is a neurodegenerative brain disorder that slowly thwarts its patient's bodily functions, perception, and sensations. With approximately 10 million people worldwide living with PD and up to 60,000 new cases each year, PD has been and will continue to be a pertinent issue in our society. Prior to experiencing the typical symptoms, many patients experience precursors like sleep problems, nightmares, loss of smell, and restlessness. Unfortunately, there is currently no cure for PD. Patients cannot terminate its impact, but merely alleviate the symptoms through medications, surgery, or therapy. Thus, early diagnosis is crucial to accelerating this process as it allows for more effective medications, therapy to slow down progression, and possible diagnosis of other neurological disorders as well. However, with the lack of laboratory tests or conclusive screenings to evaluate Parkinson's, it is only possible through neurological examinations. These examinations are not definitive though, since a patient may not meet the diagnosis criteria but have PD, or conversely, be diagnosed then realize later that they do not have PD. This therefore raises the crucial question of how we can diagnose PD in its early stages in the most effective, accurate way possible. Patients with Parkinson's typically experience a tremor in their hands or fingers, making it difficult for them to draw spirals, which is a simple task for healthy people. Thus, spiral drawing classification is considered a possible method to test for PD, but it has yet to improve. As it is typically difficult to gain access to large quantities of data from PD patients, the limited size of the data set lowers the accuracy and functionality of an algorithm in a deep learning system. However, an anomaly detection algorithm can help overcome this hindrance. This algorithm only requires data from healthy people and thus can be accumulated without much difficulty. Using this method, a more accurate method of diagnosis can be developed and implemented in hospitals as well. Overall, our investigation consists of two main parts: the conventional spiral drawing classification and anomaly detection. The data is comprised of spiral drawings from 62 PD patients and 15 healthy people, and was created through the LCD monitor and digitized pen of the Wacom Cintiq 12WX graphics. This software recorded handwriting drawings and allowed for the testing of coordination on PD patients. Since the deep learning algorithms require a huge amount of datasets, the data augmentation was applied. Image data generator from Keras library was utilized and more than 4,000 images were generated. Hyperparameters such as rotation range, brightness range, and rescale were utilized for creating various datasets as well. VGG19 is a convolutional neural network-based transfer learning algorithm. It consists of a total of 19 layers, 16 convolutional layers, and 3 fully connected layers. Unlike the basic CNN models, the VGG19 was trained with a large dataset called ImageNet, and then the trained layers got frozen to save the weights from pre-training. The pre-trained VGG19 model could be downloaded from the Keras library, and the input size should be 224 by 224. The Generative Adversarial Network, GAN, is an unsupervised learning algorithm which does not need any label or target in the dataset. It was proposed in 2014 by Goodfellow, and the model consists of two parts: the generator and the discriminator. The purpose of the generator is to create plausible data, while the discriminator aims to classify whether the data is fake or real. Since the GAN is based on solving minimax problems between the generator and the discriminator, unstable training is a critical limitation of the algorithm. Therefore, a deep convolutional generative adversarial network, DC-GAN, was proposed to resolve this downside. The DC-GAN eliminated fully connected layers in the ordinal GAN model and replaced them with the convolutional layer. Furthermore, batch normalization was applied to the model to enable stable training. Anugen was proposed to resolve the data imbalance problem with the unsupervised learning approach. The overall architecture of the model is similar to DC-GAN, but the generator in the Anugen only gets trained with the normal datasets. Furthermore, the residual loss and anomaly score are calculated between the generated standard data and anomaly data. The initial classification resulted in an accuracy of around 83%. As shown in the graph above, there are abrupt variations in the value of the training and validation loss. As a result, the values of training and validation accuracy shown on the right are inconsistent and fluctuating. After adding the batch normalization layer to the original algorithm, the accuracy increased to 92%. Furthermore, the values of the training and validation loss showed a general downward trend with less fluctuations. As a result, the training and validation accuracy also showed a general increasing trend with less inconsistency compared to the initial classification. With the anomaly detection, a large anomaly score of over 30,000 is produced when the spiral drawing of a patient is put in the system. The aberrant parts of the drawing are marked in red as shown in the picture on the right, and in comparison, for the spiral drawing of the healthy person shown on the left, the anomaly score produced is less than 1/10 of that of the PD patient, and there are no anomalous parts marked in red, demonstrating that the system successfully differentiates the two categories. Once the spiral drawings are accumulated in the database, VGG19 and antigen are used. When the patient's dataset is not large enough, antigen detects the anomaly data or the patient's data through normal datasets and along with VGG19 trains the system to classify the images. After cross-checking and feedback has occurred, the algorithm can successfully differentiate between the spiral drawings of healthy people and PD patients. This cross-checking process enables a higher accuracy despite the large amount of PD patients' data available in the status quo. Therefore, this algorithm can allow clinics and hospitals to diagnose their patients in a more accurate and efficient way. While an existing study using the spiral test and the CNN algorithm had an accuracy of 88%, our system with VGG19 had an initial accuracy of 94%, demonstrating its viability. The effective anomaly detection through antigen allows for a more accurate differentiation between healthy people and PD patients, making it a feasible and dependable method of diagnosis that can be applied in clinics and hospitals. While this algorithm was applied specifically to the spiral drawing test, it has potential to be applied to other methods of detection such as MRI data as well. Furthermore, we aim to establish a definite threshold for the anomaly score by which PD patients will be diagnosed. Thus, the system put forth in this study has potential to be implemented in hospitals in the future. And once implemented, it'll make significant changes in the ways we approach the diagnosis of PD. Thank you for your attention.